And I'm recording, and I've got audio, and let's get busy. We talked last time about the electric field and the relationship between the potential and the electric field, and how, because it's a conservative field, the conservative force, we can define the potential as in relationship to the work done against the field or by the field. And if the work is done by the field, it's the negative. The change in potential is the negative of the work done by the field, or the positive of the work done against the field. So if you do the work to move the particle in the field, it's positive work. If the field does the work to move the particle in the field, it's negative. Or it's a negative change in potential. And you have to keep straight whether that means whether the sign of the charge that's being pushed against the potential field is positive or negative. Now, the effects of any charge distribution can be described either in terms of electric field or in terms of electric potential. Electric potential is often easier to use because it is a scalar, whereas an electric field is a vector. Y'all have all learned that in the last lab series, the last 2 weeks' labs. There's an intimate connection between the potential and the field. Let us consider the case of a uniform electric field between two parallel plates. Okay. They talk about the potential between two parallel plates. What we drew. Positive and a negative. The E field is it's uniform between the plates as long as you just ignore as long as you stay away from the edge where fringing effects come into play. And then they talk about the work done by the field to move a positive charge, Q, from a point A to a point B. And that it's equal to the negative of the change in the potential energy. Okay. Let's write this out. Work equals the negative of Q, not a G. Right there, all I'm doing is I'm making the point that the difference between the potential at point B and the potential at point A is denoted V, B, BA, sub BA. And in other words, I talked about last time, you can only talk about potential relative to some other potential. And normally that would be ground. You measure the voltage relative to ground. But in the general case, you're measuring the potential difference between 2 points A and B. In this case, A and B here. And so rather than write out this whole parenthetic thing every time, just shorten it to the potential difference between point B and point A. Now, we can also write the work done as force times distance, where the force on Q is Q times E. And that force is multiplied by that distance. Where the distance here, D, is the distance from B to A. between the points A and B. Now, from these, realizing that all of these are equal, these are all the same expression, equal to the work done, either by the field or against it, what we find is that minus Q times the potential difference between B and A, the voltage from B to A, is equal to minus Q times E times the distance from A to B, or B to A. And if we divide both sides by minus Q, we get the definition of the voltage difference between point A and point B is equal to the electric field times the distance from point A to point B. Okay? Well, what happens if we divide both sides by that distance? We get voltage from A to B divided by the distance from A to B is equal to that electric field. Now look at the units here, because this is one of the places where this can get kind of confusing. So I want to take a minute and go through these step by step. What do we have here in terms of units? We have volts per meter. Which is the unit, that means our electric field is volts per meter. But we also already know that we can write we've already seen that we can write the equation for that electric field as what? The electric field generated by a point charge, K times the charge, divided by the distance squared. Okay? That means we have volts divided by distance is equal to K times Q divided by distance squared. Everybody with me so far? Well, what happens if we multiply both sides by that distance? We end up with, we've got volts divided by distance is equal to KQ over D squared. We multiply both sides by D. We end up with voltage, the potential from a point charge is equal to K times Q divided by distance. So where the E field varies as distance squared, the potential varies just inversely to distance linearly. Now, we got all kinds of units here. So let's look at these. What did we start off with as our units of our E field. Newtons per Coulomb, right? Not quite. But we can multiply newtons per Coulomb times meters per meter, because meters over meter, a meter over meter is just unity. Anything divided by itself is 1. So if we put meters on top and bottom, we don't really change anything. But we end up with Newton meters. What's a Newton meter? A Newton meter, no, not per meter. A Newton meter. No, if you take 1 Newton of force across 1 meter of distance, then you have produced 1 joule of energy. So at E field is actually can be written as newtons per Coulomb or as joules per Coulomb meter. But what's a joule per Coulomb? Right? 1 joule per Coulomb, by definition, is what? 1 volt. So a volt is a joule per Coulomb. So what we have here is joules per Coulomb meters is volts per meter. A Newton per Coulomb and a volt per meter are the same thing. Now, I've erased it, so I'm going to have to redraw it. Let's put back our plate here. We've got a nice uniform electric field between these 2 plates. And they're separated by, what's the book here? 5 centimeters. Or 0.05 meters. And what if the potential difference between them is 50 volts? What is E? E is volts per meter. So we've got 50 volts divided by 0.05 meters equals, somebody with a calculator. Works for me, 1,000 newtons per Coulomb, or 1,000 volts per meter. As long as you put it right. Yeah. The point here is that which is going to be most convenient. If you've got a problem where it says what's the E field in the center of these two parallel plates, the midpoint between them, what's the E field? Well, it's uniform because it doesn't change from one side to the other. So 50 volts divided by 5.05 meters is 1,000 volts per meter. That's your E field. You know, don't get cute trying to confuse me. If I don't see what you did, I might mark it wrong. Don't hide the answer from me when you write it out. But no, if I see what you did and I realize that it is correct, I'm not going to mark it wrong. Now, it's important to notice here that this E field is uniform and constant, all in here. Now, up here at the edges, it wouldn't be true. You have a fringing effect out here. But anywhere between these plates, it's constant and it's linear. It's going to be the same here as it is here as it is here. So all you have to do is divide the voltage by the distance, and you get the E field. What if we were talking about the potential at a point some distance from a point charge? Well, now it's not so simple, but it really is, because where did it go? Right here. You want to know the potential at some point relative to a point charge. It's K cubed divided by the distance to the point charge, by R. Whether we write it R or D, it's the same thing. It's how far away, what's the distance. From a point charge. You'll notice it looks very nearly like the E field produced by that same point charge. The only difference is if you want to know the E field, you divide by the distance squared. If you want to know the potential, you just divide by the distance without squaring it. Now, something else. Right here. Table 17.1 on page 476, which looks as suspiciously like something convenient that you would want on your index card somewhere, maybe at some point. It gives a list of breakdown voltages. I'm sorry, this is not the right table. This is typical potential voltage differences. There is a table in here of breakdown voltages somewhere. Here it is. It's actually on page 485. Table 17.3. We haven't gotten to it yet. We'll get to it when we start talking about capacitances. But you see this list here that calls dielectric strength? Those are breakdown voltages. So for air, we're going to say they give us the breakdown voltage for air is about 3 million, or 3 times 10 to the 6 volts per meter. What's the E field in this capacitor right here? Between these two parallel plates? It's 1,000 volts per meter. That's the E field generated across here. How strong would you have to get that E field before before a spark would develop across these two? Before it would arc across, before you would experience the breakdown voltage. What voltage would you have to put across here? I don't know. Let's see. You have to go 3 times 10 to the 6 volts for 1 meter. So, let me rewrite this. You're going to get breakdown, you're going to get arcing when you reach 3 million volts per meter. So you want to know X number of volts divided by 0.05 meters. When that reaches 3 million volts per meter, you're going to start seeing sparks arcing. So how many volts? 0.05 meters times 10 to the 3 million volts per meter. Meters cancel. What's 0.05 times 3 million? $150,000. Okay. So, you get those two plates 5 centimeters apart, you get them up to 150,000 volts, and you'll start seeing sparks. You've ever seen a spark jump across from your fingertip when you go to touch a doorknob? How far, what's the longest one you've ever seen? About a centimeter? About that long? You ever seen one about a centimeter long? 5 millimeters? Okay. How many volts is that? 5 millimeters would be 5 times 10 to the minus 3 meters. What's 5 times 10 to the minus 3 times 3 million? Is that right? That means you've produced a 15,000 volt potential difference to produce a 5 millimeter spark. Now, looky here on page 478, figure 17.7. Does that look familiar to anybody? No, figure 17.7. And the E field between 2 point charges. Yeah, that's exactly what that is. Well, we're going to talk about the map here in a minute. These equipotential lines, I just want to point out to you that those equipotential lines will always be perpendicular to the E field vector at whatever point you're at. So, if you calculate an E field vector anywhere at any point in space, whatever direction it's pointing at, you know that the equipotential lines associated with that E field are going to be perpendicular to that vector at that point. Now, as you can see there, they might be curved, so they're going to be changing direction at all points, but they will still be perpendicular to the E field at every point. There is one thing I want to make sure and mention to you, because it's kind of important for you to understand this. We talk about these equipotential lines or equipotential surfaces. And I don't know if you've ever thought about why they're really important. They're important for two reasons. One, because they establish the gradient. Just like the isotropic lines on this map, you can see where the gradient of the land is steepest because the lines get the equal altitude lines get closer together because the gradient of the ground is steepest. When the equal altitude lines get farther apart, the gradient is shallower. The equipotential lines in an E field are the gradient of that E field. Mathematically, that's literally a true statement mathematically, but it's analogously true as well. The topographical map is a perfect analogy for the potential lines that you draw in an E field. The steeper the gradient, the more volts per meter you have. Where did it go? There. The more volts per meter you have, the steeper the gradient of the electric field. Okay. And if that gradient gets steep enough, then the dielectric holding off the flow of electrons, in this case air, will eventually break down and the electrons will fall, will be drugged from the higher potential to the lower potential. I also want you to make mental note of this and understand what else those equipotential surfaces or equipotential lines mean. They mean that it doesn't take any work, zero work, to move a point charge from one point on an equipotential line to any other point on that same equipotential line. Okay, so if you have and thinking in terms of three-dimensional space, you have an equipotential surface. You've got a point charge or a ball that's charged up to some charge is built up on it, and it's producing an electric field pointing out in all directions, and it's got these spherical equipotential surfaces. You can have electrons or charged ions or whatever floating around on that equipotential surface. They are free to move anywhere on that equipotential surface they want to. It takes no work to do so, because the work done is equal to the change in potential. So in order to do work, you have to move it from whatever potential it's at to a higher or lower potential. Right? That brings us to this, chapter 17.4, the electron volt as a unit of energy. And I want to take our time and work through this. And I really do want to encourage each of you, if any of this doesn't make sense, stop and let's clarify it now. This is definitely going to come up in your homework and in your exams. It's the electron volt as a unit of energy. And I'm probably going to regret erasing all of those units. I have to look them up again, but we just will. I want to start over with a clean slate here. One joule per coulomb. What is that? No. Right? E field is a volt per meter. Your E field is a Newton per coulomb. A joule is a Newton meter. So, if E, we multiply this by meter over meter, then we get an E field is 1 joule per coulomb per meter. Right? But what happens if you multiply volts per meter times meters? Remember, this joule per coulomb per meter is also equal to a volt per meter. So if you multiply both sides by meters, 1 joule per coulomb is 1 volt. Okay? Now, keep all that straight, but get rid of it so we don't get it, so we don't start confusing ourselves with it. How many coulombs is 1 electron? Boom. So if you take the charge of 1 electron and you push it across 1 volt of potential difference, what are you multiplying it by? You're actually multiplying it by 1, well, in fact, let me just write that. That's equal to 1.6022 times 10 to the minus 19 coulombs times 1 joule per coulomb. So if you take the charge of a single electron, 1 electron's worth of charge, and you push it across 1 volt, you end up with 1.6022 times 10 to the minus 19 joules of energy. That is defined as 1 electron volt. The amount of energy required to push 1 electron across 1 volt of potential difference. It would be if it's a negative charge. That's when you start, generally the negative and the positive is only talking about the direction of the motion. Now again, it's you have to keep straight. Are you moving a negative charge to a higher potential or to a lower potential? The bottom line is it's negative or positive depending on whether you do the work or whether the field does the work. If the field does the work, it's negative. If you do the work, it's positive. That's what we were talking about last time. But this is 1 electron volt. And it can be an incredibly powerful tool. Did they give us an example in this work? Not really. So I'm going to give you the example. We have 1 electron. We did this, we talked about this yesterday. We've got our 2 plates. $50 volts. Somebody give me let's just say 0.1 meters, 10 centimeters apart, 50 volts. Okay, 100 centimeters. No, 100 centimeters would be 1 meter. 100 millimeters would be 0.1 meters, or 10 centimeters. Yeah, 100 centimeters would be a whole meter. Okay, so we're 0.1 meters apart. We put an electron right here and we release it from rest. Because this is the positive plate, E field's pointing that direction, the electron is going to be accelerated this direction. How fast will this electron be going? The instant it hits that, the very first instant it hits that plate. Obviously, once it hits the plate, it abruptly comes to a rest. But at the instant it just barely reaches that plate, how fast will it be going if it starts from rest? And yep, it's time to dig back into some of your Physics 1. We would, but how much energy does it have when it gets here? How much energy does it acquire? I'm talking about before it hits the plate. How much energy does it require? It acquires 1 electron times 50 volts, or 50 electron volts. Of energy. Now, the problem is electron volts are not in MKS, meters, kilograms, and seconds. Okay? But we can convert 50 EV into MKS by noting that 1 EV is equal to 1.6022 times 10 to the minus 19 joules. What's 50 times 1.6022 times 10 to the minus 19? So that electron acquires 8.011 times 10 to the minus 18 joules of kinetic energy crossing that potential. Okay? Here, it's got lots of potential energy that gets converted into kinetic energy when it goes here. Right? How do you calculate velocity from kinetic energy? One half mass times velocity squared is equal to its kinetic energy. So we've got 8.011 times 10 to the minus 18 joules is equal to 1/2. What's the mass of an electron? 9.11 times 10 to the minus 31 kilograms. Y'all do have that on your index card, right? Times velocity squared. 2 times this would be 16.022 times 10 to the minus 18 divided by 9.11 times 10 to the minus 31 equals v squared. Take the square root of both sides. What's your velocity? Multiply both sides by 2, and it becomes 16.022 times 10 to the minus 18. Here is equal to this. When I multiply both sides by 2, this becomes 16.022. Got an answer yet? Does it look like 4.2 million meters per second? Times 10 to the minus 18. Yeah. And then divide both sides by 911 times 10 to the minus 31. and take the square root. And you should get 4.2 million meters per second. How fast that little electron is going to be going when it hits that plate. A lot. Does everyone see how we did that, how I did that calculation, how I figured out how fast that electron would be going? Huh? No, but electrons are incredibly light. It would not be near that much if it were a proton, which is right where we're going. What if instead of an electron over here, we put a proton right here? What's the charge of a proton? Exactly. It would still get this much joule, this many joules of energy. But now we're going to have 8.011 times 10 to the minus 18 joules of energy. Is equal to 1/2. What's the mass of a proton? 6.7 times 10 to the minus 27? I don't start me lying. (1.6726 times 10 to the minus 27 kilograms. Okay, 1.67 times 10 to the minus 27 kilograms V squared. Multiply both sides by 2. You get 16.022 times 10 to the minus 18 joules is equal to 1.67 times 10 to the minus 27 kilograms meters squared per second squared velocity squared. Velocity squared is meters squared per second squared. Kilograms meters per second squared is what? Kilograms meters per second squared is a Newton times another meter, another distance. It's a joule. Just pointing out to you that the units work out here. We'll take them, we'll do those next. Do it slowly just to make sure. Divide this by 1.67 times 10 to the minus 27. Take the square root, and you get 98,000 meters per second. Let's look at these units. We have joules. When we multiply the charge of one electron across a 50 volts or across some potential, we end up with electron volts, which are joules. And we set that equal to 1/2 mass, which is kilograms. Yeah, the half doesn't matter, it's unitless. Times velocity squared, which is meters per second squared. Kilograms, meters, times meters per second squared. Meters per second squared is acceleration. Mass times acceleration is force, so that's a Newton meter. is a joule, which is a unit of energy. Everybody see how that works out? Class time is over. Okay, well, we did finish the week, and we did finish on time. So, hold up. Yeah, this is a point we need to talk about and be sure we understand. EVs, units. What makes it work is the conversion of 1.6022 times 10 to the minus 19 joules per EV. Okay? If you're talking about a unit of particle that has the charge of, say, something that has a charge of 6 microcoulombs. And you're talking about now that particle getting accelerated across 15,000 volts or 5,000 volts or whatever. How many EV would that be? Well, the first thing you have to do is convert coulombs into how many electrons worth of charge is that? And you get 1 electron worth of charge for every 1.6022 times 10 to the minus 19 coulombs. So, if you divide 6 times 10 to the minus 6, coulombs worth of charge on a single particle, you divide that by 1.6022 times 10 to the minus 19, you end up with 3.74 times 10 to the, 13? Times 10 to the 13 electrons across, and that you then multiply by however many volts to find the total energy that that particle would acquire. Okay, but it all hinges around that conversion, that ratio of joules per electron. Okay. Now it works easily with protons or electrons because they both have the charge of a single electron. Just be careful if you run into a problem where it talks about how many charge, some amount of charge being accelerated. You've got to make sure you count how many electrons of charge is that. That's what you multiply by the voltage, not the total charge. All right? Y'all have a good weekend. I will see you on Monday.